The next video in our field forces unit is on electric forces. We have two learning targets for this lesson, the first of which we want to be able to describe the basic nature of electric forces. So electric charge. Charge can be one of two types. We call these two types positive and negative. Now one thing to note here is there's really no reason that we had to call them positive and negative. In fact, this comes from a guy you may have heard of by the name of Benjamin Franklin. He's the first one to coin these terms. What Franklin understood, and a lot of physicists did at the time, was that there were these charges that they were opposite of each other. And so any set of opposites would have worked. Franklin chose positive and negative. Just as easily could have been on or off, or black or white. I think you get the point, but positive and negative works, okay? Behavior of charges. We know that like charges will repel each other. In other words, if I had two positive charges and they were close enough together, they would exert a force on each other such that they would push each other apart. Likewise, if I had two negative charges, they would also repel each other. Now, opposite charges, they attract. So if I had a positive and a negative charge, the forces acting on them would actually pull them together. We want to understand that everything is made of charged particles. Everything in the whole universe is. In other words, your cat is made of charged particles, your toaster is made of charged particles, and you're made of charged particles. So my question is, why doesn't everything just attract and repel each other then? Well, the reason for that is that objects are composed of equal numbers of positive and negative charges. So the same number of positives as negatives. I want you to pause the video and think about that for a second and ask yourself, what does that mean if these objects are containing the same number of positives as negatives? So you thought about this for a second, and here's a little diagram for you to consider. Notice here I have 3 positive charges and 3 negative charges, so there's the same number of each. Well, if that happens, then what that means then is that the charges cancel. In other words, if I have positive plus negative, that's going to equal a neutral charge. So the cat, the toaster, and yourself, while you are composed of charges, you have roughly the same number of positives as negatives, so you have a neutral charge to you. So you're not going to attract or repel things as you pass by them because you are neutral due to the same number of positives as negatives. So a couple of review questions here on what we've learned so far. As always, once you see the question, pause the video, answer it yourself, and then play on. First question, what are the two types of charges? Well, you know that the two types of charges are known as positive and negative charge. Second question, how do you know if two charges will attract or repel each other? Like charges, in other words, two positive or two negative charges, they will repel, while opposite charges, meaning a positive and a negative, they will attract. Last review question here. Explain why objects generally do not attract or repel each other, even though they are made of charged particles. So as we saw in the example with the cat and the toaster and yourself, we said that while objects are made up of charged particles, there are generally equal numbers of positives and negative charges in each. When there are equal numbers of positive and negative charges in each, the overall charge on the object is neutral. Hence, there is no attractive or repulsive force acting between the objects. So we've looked at the first learning target. We have described the basic nature of electric forces. Next, and this will take us a little longer, use Coulomb's law to calculate the electric force between two charges. First of all, let's talk about how we go about measuring charge and how we indicate it. First thing to notice here is up here in the title for the slide, the symbol that we use for charge is the lowercase letter q. So if you ever see that lowercase letter q, that is talking about the charge on an object or a particle. So first of all, the units on charge. The unit on charge is known as the Coulomb. And the symbol for that is the capital letter C. And yes, you'll notice in the learning target here it says use Coulomb's law. That is a person that we'll look at here in just a second. And this unit is named for this scientist. So the capital letter C is the Coulomb. That is the unit for charge. Every charge has a sign. The charge has to be either positive or negative. And so the charges use positive or negative signs to indicate that. Okay, they're always indicated with a positive or a negative sign. So some examples of what we mean by that. So say we had a charge of positive 2.7 times 10 to the negative 14th coulombs. We could either write that without a sign, and as you know from math, that by definition means it's positive, or sometimes you'll see the plus sign in it. Either of these would be the exact same. There'd be a positive 2.7 times 10 to the negative 14th coulombs. Or we could have a negative charge, and with that there has to be a negative sign out front. So this example here is negative 3.4 times 10 to the negative 17th coulombs. So now that we've seen some examples of how we go about measuring charge, let's take a look at Coulomb's law. So Coulomb's law comes from a French physicist by the name of Charles Augustin de Coulomb. And here is a picture of old Charles. No, you don't need to remember that's his picture. And you don't need to remember his name either. I think it's just interesting to put that up there. So what Coulomb discovered was that there's an equation for the electric force between two charges. And it's calculated like this. We have this equation, Fe equals K times Q1 times Q2 divided by D squared. Notice the similarity of this equation to Newton's law of universal gravitation. It's the exact same format. In fact, in the next video in this lesson, it's just going to be used to compare these two equations and to see the similarities and differences between them. Now, all the symbols, it's important that we understand the symbols here. Fe, the F with the subscript E, that's just the amount of electric force acting on an object. K is a constant, just like capital G is a constant in Newton's gravity law. K is known as Coulomb's constant, and you can see the value here, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Now you will not need to memorize this constant, nor will you need to memorize the equation. I will always give that to you. Q1 and Q2, recall that Q means charge, so Q1 and Q2 are the charge of charge 1 and charge 2, respectively. That's similar to the masses in Newton's gravity equation. And then D is the distance between the charges. So this is actually just like Newton's law of universal gravitation. They are exactly the same in the sense that they have D squared on the bottom. So let's examine this equation here just a little bit. So here's our equation up here on the right. Go ahead and take a look at that. Okay, so capital, or not capital K, lowercase k, as we said, that's Coulomb's constant. And notice it's a really big number, 8.99 times 10 to the 9th. Comparing that to Newton's law of universal gravitation, that constant is a 10 to the negative 11th. So what that tells us then is that electric forces are much larger than gravity forces. By nature, they are much larger than gravity forces. In other words, we only need very small charges to experience force. Unlike gravity, where we need really big masses to experience gravity, electric forces are not the same way. So Q1 and Q2, those are the charges. And as we've said, the unit on those are in coulombs. And the greater the charge, the greater the electric force. Just think about this. If Q1 or Q2 are increasing, that's going to mean the electric force is also increasing with it. And then lastly, on the bottom there, we have D squared. That is the square of the distance between the objects. The unit for that needs to be in meters, and the reason for that we can see in Newton, in the Coulomb's constant there, we can see we have meters squared, so we need meters for our unit there. And then just like we said with gravity, the greater the distance between the charges, the less their electric force. Just like gravity is, the greater the distance between the objects, the less the gravitational force between them. It is an inverse square relationship, as we can see there. So let's look at how we apply this equation. We have a problem here. It says, calculate the electric force that exists between two charges, where Q1 and Q2 are both equal to 3.5 times 10 to the negative 12th coulombs, that are 150 nanometers apart. Well, that 150 nanometers is 150 times 10 to the negative 9th meters. A nanometer is 1 billionth of a meter. That's what 10 to the negative 9th is, 1 billionth. So we see that in scientific notation there. So all we need to do here is use Coulomb's law, where the electric force equals Coulomb's constant times Q1 times Q2 divided by D squared. So just plugging in our numbers here, and again, you don't need to memorize the equation and you don't need to memorize the constant. The constant is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, and then we multiply by the two charges. Notice these two charges are the same. We're told Q1 is equal to Q2. which is 3.5 times 10 to the negative 12th. That's why both of these are the same. Also notice that both of these are positive. Okay, there's not a sign there, so we know that means they're positive. We'll talk about that here in just a second. And then we divide by the distance squared. Notice our distance here, we want to use the one with meters in it. We have to use meters because meters is what's in our constant unit, so we need those to cancel. So we plug all that in our calculator. Notice that meters will cancel, as will coulombs. We'll be left with newtons, which that makes sense for a force, and we get 4.89 newtons. If you haven't done this yet, go ahead and pause the video and practice plugging this in your calculator. Make sure you can get it in there correctly. Now the last thing to notice here before we go to the next example is the fact that this force here is positive. Okay, and recall we said when we were talking about gravity that negative forces indicate attractive forces. So a positive force indicates repulsive forces, and that's exactly what it should be because these are both positive. They're like charges, so they will repel each other. Okay, one more example here. It says use the diagram below to calculate the electric force acting on the two charges. Well, here are our two charges, just represented by 2 points. And then we have Q1 is 8.7 times 10 to the negative 14th coulombs. Q2 is negative, notice the negative there, negative 6.8 times 10 to the negative 13th coulombs. And then the distance between them is 28 times 10 to the negative 9th meters. So this is really the exact same problem we had on the previous example, just instead we're given a diagram like you see here instead of the text. And so we're going to use Coulomb's law, just a matter of plugging in our values. So I can plug in those values, and notice this time the two charges are different. Okay, in the first example there, they're the same. Q1 is the 8.7 times 10 to the negative 14 coulombs. Q2 is negative 6.8 times 10 to the negative 13 coulombs. Then our distance there we can see is different from the first example. So pause the video, plug this into your calculator, make sure you can get the right answer. The answer I get here is a negative 0.678 newtons. Ask yourself, why is that negative? The reason it's negative is because these two charges are opposite. One of them is positive, one of them is negative, so that means the force will be attractive. Thus we get a negative electric force there. Those two charges will be attracted towards each other if they are in fact this close together as we're seeing here. Alright, and there's my note there on the negative force, means that the force is attractive. Alright, that was the last example. Just one review question here. So as always, pause the video, answer the question, and then play it, see if you got it right. So two charges are 175 times 10 to the negative 9th meters apart. And just realize here I left out the unit meters. That there should say meters. The values of the charges are Q1 equals negative 2.8 times 10 to the negative 10th coulombs, and Q2 equals 8.4 times 10 to the negative 10th coulombs. Will the force between the particles be attractive or repulsive? How do you know? Determine the amount of electric force acting between them. So pause the video, answer the question. Alright, you've taken a few minutes here to work through this. The first part here, will the force between the particles be attractive or repulsive? Well, here's my answer. The force between the charges will be attractive. I know this because they are opposite charges. Notice Q1 is negative and Q2 is positive. So that would lead them to be attractive, and we'll see if our calculation matches up to that. Alright, second part. We're asked to determine the amount of electric force acting between them. So we need to use Coulomb's law here, which we've seen before. So here's our equation. Fe equals K times Q1, Q2 over D squared. We can just plug in our values, where K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And we plug in our charges and our distance. So you plug all that in your calculator, and you get an answer of negative 0.0121 newtons. Now again, that's negative because the force is attractive. Alright, so in this video we have described the basic nature of electric forces, and we have also shown how Coulomb's law works to calculate the electric force between the two charges that we might have.